So our speaker today is my friend Andreas Thom, and the title, you can see it on the screen, is Aspects of P-adic Operator Algebras, Joint Work with Anton Klaus-Nitzer. Please, Andreas, go ahead.
Yeah, thank you very much for the invitation, my friend Willy Cortinas from Buenos Aires. I'm really glad to speak in your seminar. And I want, so this is a completely informal talk, right? So I really want to present the ideas why I have been motivated in looking at p-adic operator algebras. I will give you some of the results. I give you hopefully a lot of examples so that you can see what things work out and what things are just more complicated or just complicated in a different way. And in order for this to be useful for you, please interrupt me at any moment with questions, and so don't hesitate. So for me, is no point in reaching any result at the moment that I want to present. I want it to be useful for the audience, so that's my point. So what is the motivation? So the motivation is basically the following, that in the study of group rings in characteristic 0, these methods from functional analysis have been very, very useful. And I will give you a few simple examples. And one example is the following. If you have a gamma discrete group, so a countable group, I'm thinking of the integers, if that's not what you usually think of, so think of an infinite group like the integers, then many people are interested in the complex group ring, which is the set of formal linear combinations of group elements. And so these are finite linear combinations. So you take the group basically as a basis, you form a vector space with basis given by the group. And this object is a unital ring, which has a multiplication just extending the group multiplication. So it's you multiply these basis vectors just as you would multiply the group elements. And any vector space on which the group acts becomes a module over the complex group ring if it was a vector space over the complex numbers. And so the representation theory of the group is encoded in the modules of this group ring. And it's quite obvious that you would expect that many properties of the group are encoded in the ring theoretic properties of the ring. And also the ring theoretic properties, they should just be important in themselves. So this, so there's, for example, one theorem that one can prove, which is a ring theoretic property. If you have A and B in the complex group ring, and A times B is equal to the identity, so the unit is just the linear combination which has 1 times the neutral element, so I write this as 1, then this implies that also B times A is equal to 1. And that is a non-trivial result. So it has nothing to do with left inverses being right inverses. It's really the question whether left invertibility implies right invertibility of an element. And that's in general not true in an arbitrary ring. And it's quite amazing that one can show it for the complex group ring. And so if you look at this very concretely, then you would write out this A as a sum of group elements with coefficients, and also the B is sum of BG G. And then you can just multiply A times B, and so this is the sum over G, H, A, G, B, H, G times H, where this G times H is considered to be one group element. So this, you can sum the coefficients that belong to the same group element in one coefficient, so it simplifies. And so one can, I can write that formula. So it's sum over all the G's, and then you have sum over coefficients A, let's say H, B, H inverse G. So that's the sum over H. times G. So now you have collected all the coefficients that belong to one group element in one thing. And if this is equal to the identity, this just means that these sums over H for each individual G, they are either trivial if G is a non-trivial group element, or they are equal to 1 if G is the neutral element. So that's a very concrete meaning. And if you look at these linear conditions that you get on AH, BH inverse G, it's a bunch of linear equations satisfied by these coefficients. It has a very, very concrete meaning to say that now B times A is also equal to 1, right? And you see that the sums that you have to consider, if you consider B times A, they are completely different, right? So the ring is non-commutative, and the sums that you consider to compute B times A are just different. And there's no like direct, short, easy argument to prove that B times A also has to be equal to 1. And so this is a very hard problem if you start looking at it as a combinatorial problem of coefficients. And now the amazing thing is that this complex group ring, it can be studied using analysis, and it can be studied using what is called the left regular representation, which is a representation of gamma as unitary operators on a Hilbert space L2 of gamma, which is squares gammable complex valued functions on gamma. And this action is just given by the left multiplication on the group, right? So this L2 gamma is, if you want, the span or orthonormal span of these delta gamma or delta G, I call them G in gamma, and then shifting the basis according to the group multiplication defines a unitary operator, just preserves the norm. And so this also gives a representation of this complex group ring as bounded operators on L2 of gamma. And you can define the reduced C-star algebra of gamma as the norm closure of the image. So that's a certain algebra of bounded operators on a Hilbert space closed under involution. That's a C-star algebra. And has an important property. It has a trace. So the trace is a functional from the reduced C-star algebra to the complex numbers. It's called a trace, and it's defined on an operator as a certain inner product written like this. So with respect to the spaces given by group elements. And it's called trace because it satisfies the usual trace equation. Trace of AB is equal to trace of BA. And it also has various other properties. So it's unital, sending the identity operator, which is in the reduced C-star algebra, to 1, and it's also positive. And it's also phaseful. So there are a few properties that you might know from the world of C-star algebras. And the embedding, there's an obvious embedding of the complex group ring inside the reduced C-star algebra of gamma that allows you to take these two elements AB that you have and study them as operators on that Hilbert space. So you really bring in some non-trivial analysis at this point. And right, so now I can sketch you the argument why this BA equal 1 also holds. And the argument is as follows. So BA, if you call this P, then P square, I can compute it, is BA, right? AB is equal to 1, so this is again BA, so this is again P. This is an idempotent. And on the other side, also, you can compute the trace of P, which is the trace of BA, right? The trace equation is the same as trace of AB. Is the trace of 1 is equal to 1. And so you got an idempotent which has trace equal to 1. And from the property that this is actually a C-star algebra and the trace is positive and faithful, basically these two properties, you can conclude that this P must be equal to 1. So this uses some C-star algebra theory. Right? It's not that complicated, but needs some more arguments. Right, and so I think that's a really, really striking application of analysis to something purely combinatorial, a question that is purely combinatorial in the study of complex group rings. And yes?
May I ask a question? I don't need to qualify it as stupid because that's understood. But when I write the equations for the element A and the element B, so that AB is 1.
Yes.
And then I write the equation so that BA is 1. And if A and B live in a commutative ring, such as the complex numbers, I seem to be getting the same.
Well, let's see. So
I'm sure this is very stupid, but just to clarify.
Well, I think it's the key point. If you think you're getting the same anyway, then there's no use of these C-star algebra techniques. But let's see. So the condition, let's write it out. AB is equal to 1. This is equivalent to saying that for all G, the sum over A H B H inverse G is equal to
delta G1, the canonical value.
Yeah, like this. Are you convinced this is true?
Mm-hmm.
And now BA equal 1. Mm-hmm. That's equivalent to saying that for all G, the sum of BH A H inverse G is the same thing.
Yeah.
But
if you can permute A and B.
You can interchange this. That's true. It's a commutative ring. So you have BH.
Yeah, and isn't okay.
So it's a sum over H.
Okay. Yeah. Okay.
So it's a different
one is the sum of S times T equals G, and the other one is the sum of T times S equals G.
Exactly.
Great.
So that's a different. All right, very good. I think I mean, this is a computation you have to do at one point to see that it's actually not obvious. Even many people have thought about it.
Sorry. I hope we can.
So this problem, it goes back to Kaplansky. So and also Kaplansky found this C-star algebraic argument, if I'm not mistaken. So I think he thought a lot about these problems. He conjectured that it's true for any field, not necessarily characteristic 0. And it's in fact an open problem. Let's say AB equal 1 implies BA equal 1 for AB in, let's say, a field with p elements group ring gamma. That's an open problem. So it's known for particular groups, large classes of groups, known for all Sophic groups, for example. But in general, it's an open problem exactly because this analysis site to which you can move it and do something non-trivial is missing for finite fields. And so our idea was, in fact, that there is some analytic site here that you could consider. And maybe it's actually helpful, but needs like a different type of study. So you can't do it with Hilbert spaces. You have to do it with something else. And so what I want to introduce now is first of all, the analog of the reduced C-star algebra, which uses the p-adic numbers. So p-adic number, so that's a compact ring. It's a completion of the integers. And what one can consider is the ring C0 of gamma with values in ZP. So let's think about that for a moment. So gamma is still this infinite discrete group. Now I look at functions. So that's a certain ring of functions from gamma to ZP. But I want that if G tends to infinity, f of G tends to 0 in ZP. So it's a topological ring, ZP. It's topologized by a nice metric. And just in the metric sense, as soon as you go out to infinity, you want that it converges to 0. So it's divisible by p more and more. That's what it means in terms of the ring structure. Okay, so that is first of all a set. The way I defined it, you can think that probably you can add elements in this ring, and but what is really interesting is that there's also a multiplication. So there's a multiplication just as for the complex group ring. So in fact, you have the group ring with p-adic coefficients that embeds in this C0 gamma ZP ring as a unital subring. So it's basically a completion of the finitary functions on which the convolution or the product obviously exists to some p-adic object, so to some completion. So this is the, one can call this the p-adic group algebra. And there's an important structure. So there is, you can restrict mod p, and the restriction mod p defines a homomorphism from this group algebra to the group ring of gamma with coefficients in the finite field, the purely algebraic group ring. And so that's the bridge to the problem that I was just mentioning, right? So if you want to understand algebraic properties of this group ring over a finite field, for example, properties of idempotence or properties of other elements, you can now try to lift them to this p-adic group algebra and then try to use analytic methods to analyze them. So for example, and it's not very hard, so that's a lemma. I think it's well known in this area. So if E is an idempotent, so let me, sorry. An idempotent, then there exists E tilde in C0 gamma ZP, idempotent, so that the restriction mod P of E tilde is equal to E, and this E tilde is in fact unique up to conjugation. So it's not a priori, it's not unique, but it's unique up to conjugation. So for many purposes, it's actually unique, right? So for example, this there's now also a natural trace on C0 gamma ZP, taking values in ZP. And this, if you have a function, you would send it to the value at the neutral element. So that's the natural trace that also exists on this p-adic group algebra. And from the lemma, what the lemma implies that the trace of this E tilde only depends on E. Right? The lift is unique up to conjugation. If you apply a trace, then it doesn't matter which element in the conjugacy class you take, you always get the same trace. And that's really surprising because that's an element in ZP. right? So even though you started with an idempotent in the group ring over a finite field, you now got not just its coefficient at the identity, which is the trace that you also have in the finite field, but there's a unique lift of this trace, right? So let me write this. So there is the trace down here, and there's ZP, there is reduction mod P, and then there exists a unique lift of this trace to ZP, which gives you an invariant of an idempotent which has much more information than just the usual trace. And the conjecture, so my favorite conjecture, personal conjecture, is that if E in FP is an idempotent with the property that the trace of the lifted idempotent is equal to 1, so as an element in ZP, then actually this E is equal to the neutral element in FP gamma. So that's the C star. I mean, that would be beautiful because it implies this Kaplanski conjecture for group rings over finite fields, because it's exactly this missing step that there's some mechanism that allows you to detect from information about traces that certain idempotents are actually equal to 1 or equal to 0 or something like this. So that's and there's no counterexample to this conjecture. And I think my original motivation was to find a p-adic setup where a theorem like this could be proved, just as the analog for C-star algebras could be proved if you knew enough about Hilbert spaces. So that was the motivation, and I think there's still some chance that this program in some way or another will work out. But what I have found in my this joint work with Anton Klausnitzer is that somehow a lot of things are quite different, and somehow the intuition that one has from the theory of Hilbert spaces is not, I mean, you cannot adapt it in a really, really straightforward way. So it's really a little bit more complicated, and different tools have to be used. But we made some progress, and I want to report about that progress. And I would be happy if you have any questions also to explain more about any part of.
What is question? Sorry.
Actually, were you talking?
I was about to ask you ask something, but you can go ahead. I mean, I just wanted to say maybe this conjecture is even equivalent to Kaplanski conjecture. Or the FP, I mean.
Yeah, maybe. Yeah, maybe. I mean, it kind of points in a different direction, but yeah, might be equivalent. You're right.
Because if you find,
I'm not sure. Maybe it's
an example for this invertibility. I guess you find some idempotent there, right? Where the trace is not 1. No. Yeah, I don't know.
I think maybe the conjecture is actually stronger because I'm saying something about all idempotents, whereas Kaplanski's conjecture is only saying about these AB type of constructions. So maybe it's a stronger conjecture.
Okay. Yeah.
I have another question. So this process of lifting the idempotent to another idempotent, and this be unique up to conjugation, it seems to me that it works for general algebras, right? That if you have p-adic lift, then it works. So this says that you always have a Chern character going from the K0 of the algebra where the residue field to say basically components of the algebra above of the p-adic algebra.
I think this has to do with the fact that I'm not an expert on this, but I believe that the topological Hochschild homology of FP is ZP. something like this. So I think it has to do with this extension of the character into this direction of topological Hochschultomology. But I'm not an expert on this.
Yeah,
so I talked with
what I say is any function, any linear function that is defined on idempotence and that gives the same result when you conjugate, we have this property. And this is true of the chunk character to use on.
Oh, I see what you mean. Yes, yeah. Yeah, I think this has some like, I think you are completely right. What I wanted to say is that these p-adic valued invariants for FP algebras are not completely unheard of. So because this topological Hochschultomology has this flavor already. And I think there's even a relationship, but I'm not sure about what it is exactly. So what we wanted to do is to first of all find a good space on which all these algebras act. And we liked Hilbert spaces, and the particular feature of Hilbert spaces we liked is its self-duality. So whenever you have a linear functional on a Hilbert space, it is given by the inner product with a vector. So this is the Ries representation theorem. And we were looking through the literature and we couldn't find, and I think there is no Banach space over QP, which has this property. There's no nice L2 completion of something, but what we could find was a locally compact abelian group that has this self-dual property, and I will explain you how that goes now. So that's the following. So if X is just a countable set, then I define QP of X to be the functions from X to QP, so these QP p-adic numbers, so that the norm of f of X, so that has a p-adic norm, and if it's less than 1, that's exactly when the value takes, when the value is a p-adic integer, almost everywhere. So almost everywhere, meaning that it only fails for a finite set, right? So this is quite obviously it's just a subset of the product of QP, but you have restrictions, right? So you only want values that are really in QP, not in ZP, for finitely many coordinates. So that's also known as the restricted product. And there's the restricted product with respect to a family of compact open subgroups, which are just the integers, p-adic integers at this point. So it's very reminiscent of the construction of the Adele space, if you have seen that. So if you start with the rational numbers and look at all the completions, then you would also not take the product of all these completions, but you would take the restricted product. And that would be the right object. That would be, again, a locally compact abelian group. It would contain the rational numbers as a discrete subgroup. And here it's kind of similar, that this restricted product is a natural object to consider. And so this QP of X is a locally compact abelian group. It is also metrizable, so it's second countable. And what is important is that it is self-dual. So self-dual means that in the sense of Pontryagin duality, you can always consider for a given locally compact abelian group its Pontryagin dual. And sometimes it's the same group up to isomorphism, and sometimes it isn't. So for the real numbers, for example, the Pontryagin dual is the same. For Z mod P, it is the same. But for S1, for example, the Pontryagin dual is Z. so the integers, so that's different, right? So and in fact, there's even a classification of torsion-free, locally compact, self-dual abelian groups. And the only ones that exist are the real numbers or products of the real numbers. And then this object, the object that we have defined here, so indexed by some infinite countable set. And then there are a few more examples which are rather artificial if you take just basically the product of one thing with its dual. That's also isomorphic to its dual, so but that's not so interesting. So here it's really self-dual in an interesting way. And I can tell you the pairing is very concrete. If you write out, right, so this is the replacement of the inner product basically that you have on a Hilbert space. It's now a pairing taking values in S1 because we built our duality on homomorphisms to S1. And if you take one function and another function F2, F1 and F2, then what you do is you take the sum over all x in x, F1x, F2x, integers, right? And so that's a finite sum by assumption, because for both F1 and F2, there's only a finite set where it really takes values outside of the p-adic integer. So in a natural way, it's an element in QP modulo ZP, right? So that's where it lands. And this is very easy to express. So that's the same as Z1 over P divided by Z, because you don't have to complete essentially. And this, in fact, is in a very natural way embedded in S1, because this Z1 over P has a natural homomorphism to the real numbers. And so if you divide this by Z, it has a natural homomorphism to R mod Z. So there's really, so it's really, I think, somehow important that there's really a preferred map here, and there's a canonical map induced mod Z, and then really this inner product, it doesn't depend on an embedding of this Z1 divided by P, because we choose this preferred embedding of Z1 divided by P into R. I hope that makes it clear that there's really no, it's very canonical, this. And so this pairing, it shows up very naturally, is this duality pairing. So it's this, the reason why the group is self-dual. So any homomorphism from QPX to S1 is given by inner product with some other vector in QPX. So that's basically the analog of the Rees representation theorem. So that's kind of very nice. And so we think of this object as really some analog of a Hilbert space with orthonormal basis given by X, but in a p-adic setting. So,
I mean, you remark that QP mod CP embeds in the usual S circle, but in what follows, do you care about the rest of S1, or will you use QP mod CP as your p-adic S1?
Well, I mean, in order to define the Pontryagin dual, I think I do need the topology on S1. But maybe all these homomorphisms are automatically continuous, could also be. I mean, I'm not sure completely whether this is a relevant part of the information. Because no, I think the rest of S1 doesn't play a big role at this moment. All right. And so what now comes up very naturally is to take a B of QP X to be Well, the bounded or continuous, let's say, homomorphisms from QPX to QPX. So QPX is a abelian group. T is a homomorphism of abelian groups. That's very natural. That should be the replacement of the bounded operators on a Hilbert space, right? So all the homomorphisms from this locally compact abelian group to itself. That's what it is.
Doesn't it bother you that it's not the QP vector space, or is it?
Well, I got over it because I was looking for a QP vector space for very long and couldn't find one. And now I was very happy to find this self-dual object. And I thought, aha, maybe I have to give up my requirement that it's a QP vector space in order to gain something positive, which is this self-duality.
Right.
But it bothers me a little bit.
But is it also not a CP module, or is it?
It is a CP module.
So you can tensor it with QP if you want.
You can tensor it with QP, but that's right. Yeah. Tensor it with QP, but it's the essential part is this. I mean, if you tensor it with QP, so if you look at this pairing and the way I defined it, I'm taking mod ZP, so that if I tensor with QP, then this is kind of not working anymore. So this inner product does not extend to the tensor product over Q with QP. But of course, you can do that if it helps. All right, so there's now, I mean, there are various natural topologies that you can now put on the bounded operators. And these topologies, they resemble essentially the strong operator topology, which is the topology of pointwise convergence. You can also speak about the weak topology, where you would require some convergence with respect to this pairing. And then there's also the norm topology, where you would require some compatibility with the natural norm that you carry on, that you have on this object here, which is just the supremum over the norms of all the values, right? So that's yes, it's the supremum over all the norms of the values in this case, right? So there are these various topologies, and you can consider closed subalgebras in various topologies, and yeah, you can start looking at this for a little bit, but it turns out that a lot of these things, as they usually do in p-adic analysis, they coincide. So in the end, there's no difference between C0, L1 functions and L2 functions, and there's also, in this case, there's no difference between for example, there's no difference between the group C-star algebra and the group von Neumann algebra. Even that is the same, as it turns out. So a lot of things coincide, which is good because it's easier, but it's also bad because something interesting, some interesting.
So you say that all these natural topologies coincide?
Yeah, the topologies are different, but the completions are the same.
Uh-huh.
And also I mean, for example, I mean, let me give you an important piece of additional information. So there is now, okay, let me start a little more slowly. You can now look at QP of gamma. So that's the restricted product of QP indexed over gamma. It's our p-adic analog of L2 of gamma. And there's a natural action of gamma on this, just shifting the index set around. And you get a natural representation, lambda tilde, of C0 gamma ZP in the bounded operators of QP gamma. All right. So that's a natural representation. And And so there's no, you can't complete it anymore. It's already, the image is already complete. So that's one bit of a problem. And also, if you look at the set of operators that commute with this algebra, it's the same algebra acting on the other side. So there's really no difference between the group C-star algebra and the group von Neumann algebra in this setting. So so that's a theorem.
The double commutant is the same.
Yes, let me write these two statements. So the image is already closed. And its bicommutant is, that's just the same thing. So the bicommutant is the commutant of the commutant. So it's in von Neumann algebra theory, that would be the strong operator topology closure of the C-star algebra, which a priori would be even bigger, but in this case, it's
but so did you finally decide on a topology for BQP gamma?
Did we what?
You mentioned that there were different topologies that you could put in BQP gamma, and you said, yeah, but the completions are all the same. But so you choose one or not? I mean,
but if I say closed here, I say that means norm closed.
Okay.
Yeah, exactly. Yeah, I choose one. All right, and so that seems, I mean, gives some sort of way of representing this p-adic group algebra on some sort of a Hilbert space, but we are still, I mean, we are still, well, lacking the tools of using it for anything, because we don't have these notions. I mean, we don't even understand the single operator on this bound in this algebra of bounded operators. And so that's what we were looking at in this paper with Anton Klausnitzer. And we were looking at a very natural problem. So let me write it like this. What about a single operator? And what is very, very important in C-star algebra theory is, for example, the functional calculus. So there's an operator, and then there are natural conditions. So, for example, you could say operator is self-adjoint, or it is more generally normal, right? So you have two natural conditions that imply that there is basically a homomorphism from the algebra of continuous functions on the spectrum of T to the bounded operators on, let's now write L2 of N, right? I should write this in parentheses. So T is a bounded operator on L2 N. So there are very easy algebraic conditions involving T and the adjoint of T that imply that somehow the canonical map that you have sending from the polynomial ring, sending T to T, extend to the continuous functions on the entire spectrum, which is a complex set of the complex plane. That's very useful. That's used all the time. And so we were looking, is there anything like this for operators on our p-adic Hilbert space? So first of all, what is possible is to define an involution. So B of QPX has an involution. So there is, it's very naturally defined in terms of this pairing that we have. So as soon as you have some self-duality, you have an involution. that's not so complicated to see. But we couldn't find a condition that would involve the involution and would ensure the extension to some sort of algebra of continuous functions. But we could anyway characterize operators that do have an extension to some algebra of continuous functions. And let me present this as a like sample theorem, which tells you how things can become more complicated. And so I don't want to start with a theorem. I want to start with definition. If you have an operator on this QPX is called, and so then now we chose this name because it resembles properties of normal contractions on Hilbert spaces. So it's called a normal contraction if for all n in n, you can define the following operator: t times t minus 1 times t minus 2 up to t minus n. And you divide that by n factorial. So that's, sorry, you go only to n minus 1. So there are n factors on the top, and then there are n factors on the bottom. So this basically can be defined and is a contraction. So okay, so what does it mean can be defined? Well, can be defined means that usually you can, of course, take this product t times t minus 1 times t minus 2 up to t minus n minus 1. So that product, that's okay. But if you divide by n factorial, that's not an operation that you have on all of the operators on this locally compact abelian group. So some of them you can divide by n factorial, and then that just means there's another operator, so that this operator times n factorial is the one that you have already there. So there's no mystery, but can be defined means that this operation of division by n factorial can be carried out on that particular operator. And well, then it is a unique operator that is defined, and this operator should be a contraction. So starting with n equal to 1, this means that t itself is a contraction. For n equal to 2, it means that t times t minus 1 can be divided by 2, and the result is a contraction. So there's a kind of all kinds of conditions that you get. Okay, so it's quite complicated somehow, but the theorem is the following. So if t is a normal contraction, if and only if you look at the polynomial ring, and so you have this natural homomorphism that you always have, right? So this is the one sending t to t. So basically the ring from the homomorphism from the polynomial ring sending the generator to the operator that you want to study. And this is naturally embedded in the continuous functions from the p-adic numbers to itself. And how does that embedding go? Well, this t goes to the identity map on ZP. The identity map is an element in this ring of continuous functions from ZP to ZP. It maps a point to itself. And the theorem is it's a normal contraction if and only if there exists an extension here. And in that case, it's also a unique extension. So in some sense, this settles the problem of this continuous functional calculus, because that's exactly what you want, right? You have this operator and it's a contraction, so its spectrum should be inside ZP in some sense. And now you want a continuous function on ZP applied to T to make sense. And you want a condition when that is always possible. That's exactly what continuous functional calculus means. And being a normal contraction characterizes this property. So it's not just an absolutely complicated condition that implies it, but it's in fact equivalent. So, yeah. Okay, and so that shows that, I mean, unfortunately, it shows that many operators that you like do not satisfy this. So many, I mean, it's not so easy, in fact, to write down even a single normal contraction. I can, so in our paper, there are various examples of this, but it's usually the algebras that we consider, they are.
Yeah, but I have a small question.
Yeah.
I mean, there are closed subsets inside CP that are not CP.
Yes. Closed and open.
Yeah, and so if I want, I mean, if you have in real life, you have an operator and you have that is, say, normal, and then you have this map from the continuous functions on the spectrum, which need not be all the complex numbers, right? So,
yeah.
I mean, so this would look like these are the ones, these are the ones whose spectrum is the whole of CP or something. And then there might be another theorem that characterizes those so that the map extends to continuous functions on some closed subset of CP.
Yeah, that might be. Yeah, I mean, yeah. So, I mean, this is only for contractions. So contractions, but that's somehow the same here. If you look at this setting, if you just assume it's, let's say, a self-adjoint contraction, then that's equivalent to saying that you have a continuous functional calculus on that part of the real numbers, for example. And then for particular contractions, you have even smaller algebras on which this is well defined. That's right. Okay. Yeah, and we try to use these. I mean, another result that we obtained is.
I have a question.
Yes.
What happens if you replace continuous functions with analytic functions? Do you then get more operators which satisfy that kind of functional calculus?
Oh yes, I think if you take analytic functions, then it's much more general. Because this, I mean, everything that is like a convergent power series, it will also converge in this bounded operator. So but that, I mean, at least in my view, this more corresponds to holomorphic functional calculus, which is also more general, but has fewer applications somehow. So how much do I have? Any time left, actually, or what is the usual schedule that you have?
Well, I mean, we tell speakers to talk, to prepare to talk for 50 minutes, so as to allow for 10 minutes of questions. But
okay, I didn't read this.
You can go on, say at 5 more minutes, and then if somebody complains.
I think I will just state two theorems that you might find interesting. And so one is about K0 of the what I call the compact operators. So these are, it's really defined in a very similar way as in the Hilbert space case, that you can look at the operators whose image is relatively compact in this locally compact group. Though they form a two-sided ideal, and K0 of it is equal to the integers, and the proof is not very complicated. You exhaust it by matrices, so that part works quite well. And then there's another theorem about the K group of all the bounded operators, and that we compute to be equal to 0. And that's sort of a little bit more complicated than one might think at first, because, I mean, usually these bounded operators, that's a very flexible thing, and it's in particular an infinite sum ring if you have bounded operators on a Hilbert space. But here, because of this finite support condition, it's not an infinite sum ring. You can't repeat an operator infinitely many times. So what do? But there is a subring, so you can look at the subring of contractions inside. So that's a subring, in fact, because the sum of two contractions is a contraction in the p-adic sense. And that is an infinite sum ring. So for this one, for this B1, the contractive operators, you can argue just the way you can for ordinary Hilbert spaces. And then there's like a second step where you have to observe that an arbitrary idempotent, it might not lie in B1, but you can subtract a finite an idempotent with finite dimensional image from it, so that the difference lies in B1. So there might be a finite part where this idempotent is not bounded by 1. And on that part, you can basically subtract the finite dimensional image idempotent so that you are in a contraction. So you are a contraction. So let me write the lemma. So if E in B of QP x satisfies E square equal to E, then there exists F, and that's now in fact a compact idempotent. So it's in the compact operators, F square equal to F, and E F equal F E equal F. So it's really a sub thing. And then E minus F lies in this subalgebra B1.
Sorry.
And so you now have to, sorry?
Is E less than F or F less than E? Because what you wrote at the rightmost part of your screen, I cannot see. I read EF equals FE equals, and then I don't see what comes next.
F.
Okay, thanks.
You can't read what's on the right of the screen. That's not intended. I hope at least should be F. And so you can somehow split an arbitrary idempotent into one which has a compact image and another one which is contractive. So for the contractive one, you know already it's 0 in K theory. And for this one which is finite, you now know it's also equivalent to a contractive idempotent because you know all the idempotents in finite dimensions. So it's kind of a little bit more complicated than for the Hilbert space case, but not much more complicated. But it's kind of a slightly different argument in some sense. So, okay, maybe I'm ending here with these two computations. I hope they are the starting point for more interesting computations for semi-direct products or whatever other examples of natural algebras that you can define. Yeah, but yeah, that's the state of the art. Yeah, thank you for your attention. I hope I didn't go over time too much.
Okay, so no, well, I have 11 o'clock, so it was perfect. Okay, so are there any questions from the audience?
Yeah, I have another question. So
Yeah.
back to your original question on this Kaplansky conjecture, um, can one equivalently pose them as questions on invariance of such algebras? So, I mean, we have cyclic homology and K theory for these kind of p-adic group C star algebras. And we have shown that these restrict to the reduction mod P. So there's no difference between these invariants. So can somehow these invariants be used to answer questions like these?
I don't think, because I mean, if AB is equal to 1, then BA is an idempotent equivalent to 1, right? So so you don't need computation of K theory to deduce this, but it's really this other step which is missing, where in the characteristic 0 case or the C star case, you have a lot of structure in the trace coming from the positivity of the inner product and so on, where you can actually deduce something in the ring from the K-theoretic computation. And so this step is missing. So I think we're not missing the K-theoretic part of the argument. We are more missing this step where you would relate the K-theoretic information to actual properties of elements in the.
So the faithfulness of the trace.
Yeah, faithfulness of the trace, exactly.
And is there a tensor product? I mean, you could tensor K, right? I mean,
Yes,
compact
tensor products. There's certainly a spatial tensor product. If you have two algebras sitting in B of something, you can take basically the product of the index set, and that's a natural embedding of the algebraic tensor product in something that has a topology, and there you can complete. So that's like a minimal tensor product. And somehow we are lacking. I mean, since there's no good notion of a C-star algebra, there's no, I mean, I don't know whether one should just use the projective tensor product. I mean, there are of course other tensor products on these p-adic algebras, but I didn't think of the question whether, let's say, that the projective tensor product of two algebras can also be represented on such a Hilbert space in a canonical way. So that I didn't think of that. Yeah.
But for example, B tensor B.
Yeah.
Is that something? Does it have trivial K0? So
you mean some completed tensor product, or?
yeah, I mean when from the space for the spatial product, what you say looks like K tensor K is going to be K because 6 times 6,
Yeah.
6. But I don't know about B.
B tensor B. I'm not sure if this is the same as B, for example. Yeah, I didn't think of this. No, I'm sorry. Many open questions.
Okay.
Is there an analogous of the strong and weak topology on these operators?
Well, you can certainly. So where is it? Certainly write them down. So
Yeah, like in the usual Hilbert spaces, right? Using the pairing.
I'm still looking for the pairing. Yes, I mean, you have the pairing. Of course, you can just write the strong operator topology, the weak topology. You can define all this. Of course, the Cauchy-Schwarz inequality is missing. That makes it complicated. What still works out is things like the closed graph theorem, which helps you for some of the comparisons between different types of continuity of operators, for example.
Yeah, if you did you think about like these group algebras? They are like von Neumann algebras. Are they closed for this week? And
Well, what I said is that what is true is this thing. So
they are closed in the norm, right?
Well, if you take the bicommutant here, that's really the largest thing you could possibly think of. So whatever completion you take, it should still commute with everything which
this should be
was
weekly
already
closed, I
commuting.
guess, right?
So and even that doesn't add anything to the algebra. So it's
there should be a like von Neumann theorem for these things. Every duo should be weekly closed.
Yeah, maybe.
Closed. Yeah. Okay. Thank you.
Okay, are there any more questions? Otherwise, I'll stop the recording here.